Hello and welcome to the keynote speech for the CDS conference by LEY's Academy, the speech on network forensics. So let's get started. We're going to learn about performing network packet analysis. So we will understand what is network packet structure, the network packet capture, the analysis of the network packet, router forensics, and firewall log forensics. Here are some basics about network forensics. We understand there is a main protocol, Internet Protocol version 4, or IPv4 for short. It has 32-bit address, and it's a series of 4 decimal numbers. So it could be 107.22.98.198. This is an example of an IP version 4 address. Each 3-digit number must be between 0 and 255. So we have 107, it's between 0 and 255. The same thing is true for the rest of the numbers. We have 3 network classes, class A, class B, and class C. We also have subnetting and CIDR. We also have recently seen IP version 6, which has a 128-bit address space. It uses a hex numbering method. On our left side, we can see that IP version 4 uses a decimal notation or method. However, IP version 6, it has more address space, 128 rather than just 32, and it uses the hex numbering method or notation. Let's take a look at the OSI, or Open System Interconnection model. In this model, we have 7 layers. We start with the physical layer, number 1, moving up to the data link layer, and then the network layer, transport layer, session layer, presentation layer, and finally the application layer. So these are the 7 layers that make up the OSI model. So this is the backbone of the networking principle. Let's take a look at some of the protocols that we have at the application layer. We have the Hypertext Transfer Protocol, HTTP. Some of the messages that we might see as part of this protocol: get, to request to read a web page. So when we are on Google, for example, and we're requesting to read a web page, in the back end, what happens actually, a GET request is sent from the web browser to the web server because we are requesting to read a web page. Then we have head, request to read the head section of a web page. Push, to request to write a web page, So this might be interesting from a security perspective because writing a web page might not be something that business organizations will allow on their web server. So we have to be careful with allowing the put message. So put is to request to write a web page. Post, request to append a page. We have the delete, which means to remove a web page, which is also interesting and concerning to us from a security perspective. Link connects 2 existing resources on a web page, and link, as the name would suggest, it will break an existing connection between 2 resources. So these are some of the messages that we might see when we are dealing with web applications, and web servers through the HTTP. Now we're going to take a look at the network packet analysis. So we have network packets because data is sent across the network and it is divided into chunks called packets. So when we send a packet over the network, that packet is basically a chunk of the data. It's not the entire data. If we send an email message, for example, or if we upload a file or send a file across the network, that file gets broken down into chunks. We call these chunks packets or data packets. Packets are divided into 3 sections. We have the header, the payload, and the footer. For the headers, you can have several headers put on by different protocols at different layers of the OSI model. We saw the application layer, from the bottom, we saw the physical layer, the data link layer, session layer, network layer, all the way to the application layer. So we could have different or several layers put on by different protocols at different layers of the OSI model. Each header contains different information. Combined, they have several pieces of information interesting to forensic investigators. The TCP header synchronization bits also yield interesting forensic data. The TCP header is a forensically interesting artifact for us. Port scanning, seeing incoming packets destined for well-known ports is a telltale sign of a port scan. If somebody is trying to scan our ports to see what ports are open and what services are running. We have the payload, which is the body or the information contained on that packet. On that packet, the actual content of the packet is delivered to the destination. If a packet is fixed length, payload may be padded with blank information or a specific pattern to make it the right size. We have the trailer which contains error checking data to detect errors that occur during transmission. May be part of the Ethernet or point-to-point PPP frame or other layer 2 protocols. So at layer 2, we do some error checking. And the error checking is this is where the trailer section helps as part of the packet. We have ports, a number, which is a number. A port is a number that identifies a channel in which communication can occur. 65,635 possible ports. So that means this is how many ports we have. Not all of them are used. We usually have the top 1,000 most commonly used ports. Knowing what port a packet was destined for or coming from tells you what protocol it was using. For example, port number 80 for HTTP traffic, port number 443, port number 20 and 22, for example, for email communication, so on and so forth. Some important ports, again, 20 and 21 for FTP, 22 secure shell, 23 telnet, 25 for SMTP, 53 for DNS, 80 for HTTP, and 110 for POP3. 407 Timbuktu utility, 6666, this is the beast. And then we have other ports that are less common, less popular. We have different types of network attacks. We have denial of service, ping of death, ping flood, teardrop, sync flood, LAN attacks, MERF, DHCP starvation, HTTP post attack, PDOS, login DOS, packet mistreating. All of these types of attacks could happen on the network layer. Maybe something that we can all relate to is denial of service. This is where an adversary or an attacker will try to flood our network with unwanted traffic. Imagine somebody is trying to send too many packets to our server randomly, and our server is unable to keep up with the traffic to process or respond to all of these packets. So our server will be overwhelmed, and eventually it will stop responding. So this is an example of a denial of service attack. It could be, again, targeted at a given server, and increased traffic affects the rest of the target. So whenever there's a denial of service attack, legitimate traffic will not be able to be processed. Attacker usually floods, as we said, the network with malicious packets, preventing legitimate network traffic from passing through. Attacker will use one of these three approaches. They will damage, their approach is to either damage the target machine's ability to operate, because they will overwhelm our server, overflow the target machine with open connections at the same time, use the bandwidth to target onto the target machine. We have ping of death. The attacker sends an Internet Control Message Protocol, or ICMP echo packet of a large size than the target machine can accept. So somebody is trying to send you something that you cannot process it. Imagine somebody's trying to bite more than what they can chew. if the packet size is bigger than what the machine can handle, this will be an example of a ping of death attack. Firewalls can be configured to block incoming ICMP packets completely or block ICMP packets that are malformed or of an improper length. So that's the good news for us. Ping flood and teardrop. Ping flood will send a tremendous number of ICMP packets to the target, hoping to overwhelm it again. On the other side, the teardrop attack is where an attacker sends fragments of packets with bad values in them, which might cause the target system to crash when it tries to resemble these packets or fragments, because a packet gets assembled to create the entire message, and this is where teardrop attack might happen. SYN flood attack, attacker sends unlimited synchronization requests to the host machine, and this could overwhelm the target system with phantom connection requests and render it unable to respond to legitimate requests. We have the LAN attack. The attacker sends a fake TCP SYN packet with the same source and destination IP addresses and ports as the target computer. The victim computer will be tricked into thinking it is sending message to itself because the packets coming from the outside use the computer's own IP address. Smurf attack generates a large number of ICMP echo requests from a single request, acting as an amplifier. This will cause a traffic jam in the target network. DHCP starvation and DHCP post attack. A DOS attack. This is a type of a DOS attack. If enough requests flood onto the network, the attacker can completely exhaust the address space allocated by the DHCP servers for an indefinite period of time. For the HTTP post attack, the attacker sends a legitimate HTTP post message, and part of the post message is the content length indicating the size of the message to follow. The attacker will send the actual message body at an extremely slow rate. The server is then hung up waiting for that message to complete. We have the PDoS, permanent denial of service attack, that damages the system so badly that the victim machine needs an operating reinstall or even new hardware. This is very risky. So permanent denial of attack. Login, denial of attack service. Attacker overloads the login process by continually sending login requests. Too many login requests. We have the packet mistreating occurs when a compromised router mishandles packets, which results in congestion in part of the network, maybe at the network layer where the router works. We have some tools to help us analyze network traffic. We call them sniffers, sniffer is a software or hardware that can intercept and log traffic passing over a digital network. It extracts network packets and performs a statistical analysis on the dumped information. Commonly applied to sniffers include TC dump, Unix platform only, TC dump, Windows dump, and TC dump. So these are the three major sniffers. Of course, we have Wireshark as well. So WinDump is a version of TC dump for Windows. Both programs extract network packets and perform statistical analysis on dumped information. Wireshark is a major packet sniffer and network protocol analyzer. It works on all major operating systems, Windows, Linux, and Mac, and it's free. It supports both IP version 4 and IP version 6. This is the main screen of Wireshark. This is the packet detail section. We can see details of the packet here. And we can analyze that. We can see here. So my screen was stopped for a second. Let me share the screen again. So let me share the recording, the screen again. Okay, we should be good now. And here we have Nmap. So Nmap allows the user to map out what ports are open on a target system and what services are running. This is a commonly known command line, but it also has a Windows interface called ZenMap that's available for free. Many of us are familiar with Nmap. This is a major port scanner, network scanner. This is popular with hackers because it can be configured to operate rather stealthily and determine all open ports on an individual machine or for all machines in an entire range of IP addresses. This is the main screen of Nmap. And we should be able to share the screen here again. So this is all Nmap. We have Snort and Net Witness. These are Snort is a primarily used as an open source intrusion detection system. Net Witness is a product from RSA that has a freeware version, Net Witness. It's a threat analysis and protocol analyzer, not, of course, not as an easy to use as Wireshark. Using log files as evidence, log files contain primary records of a person's activities on a network or a system. Log files can often identify the source, nature, and time of an attack, specific user account or events related to illicit activity. Imagine this, imagine that somebody logged into our network in the middle of the night, outside of the business hours, and they logged in with a standard user account. They elevated their privileges to an administrator account. They accessed the database. They read the database. They logged out of that account. They deleted that account, and they logged out of the system. So that could be an example of a suspicious activity where a log file will be able to tell us about all of these details. We have different types of logs. We have authentication logs, application logs. We have OS logs, network device logs, and security events. Different wireless specifications here. Wireless security, we have the Wired Equivalence Privacy, WEP or WEP. It uses the stream cipher RC4 to secure the data and CRC32 checksum for error checking. It's no longer recommended for use because it's no longer secure. It could be cracked. We have the Wi-Fi Protected Access or WPA. It uses the Temporal Key Integrity Protocol or TKIP, which is a 128-bit per packet key that dynamically generates a new key for each packet. So that makes it very, very secure. WPA2 is based on IEEE standard 802.11i standard. We have WPA3, which requires attackers to interact with your Wi-Fi for every password guess they make, making it much harder and time-consuming to crack our Wi-Fi passwords. We have Wi-Fi Easy Connect to enable you to connect a device by merely scanning a QR code on your phone. And with that WPA3, even open networks will encrypt your individual traffic, which is very good. And this brings us to the end of our keynote speech. Thank you, Early Wise Academy, for the opportunity. And this is the end.